Let's look at the inverse functions in a little bit more detail. That's what we're really interested in looking at. Notation, first of all, is the negative one. Now, it's not to be confused with an index. It's not an index. So we're not saying it's the reciprocal of function x. That's the symbol for inverse function. The composite function of a function of its inverse must be x. Because remember, the inverse function is undoing the function. So it should always bring it back to x. That means if you substitute in the inverse function into the function, or vice versa, we should end up with the result x. Example of that. There's our original function, x minus 2 and x plus 2. Let's work out what the inverse function is. So I'll swap the x and the y's around, and we'll make y the subject of that. Okay, there's my inverse function. So if I substitute the function into the inverse function, playing around with the algebra, the denominators are the same there, so multiply everything by x plus 2. Sure enough, that turns out to be x. Well, let's check the other way around as well. Let's substitute the inverse function into the function itself. Again, the denominators are the same, so we can multiply that, play around with it. Yes, we end up with x once again. So domain and range, we talked a bit about that yesterday. If AB is a point on the function, then BA must be a point on the inverse function. The x and the y's are basically swapping around. That means, as we said, the domain becomes the range and the range becomes the domain. It's a simple little example. Here's y equals e to the power of x, which we know is our basic exponential curve there. Domain, we can see, is all real x. The range is y is greater than 0. What's its inverse? Swap x and y around, and making y the subject, we get y is the log of x. So therefore the domain of the log function must be x is greater than 0. The range swaps with the domain, and the range is all real y. Domain swaps with the range. And sure enough, if I was to draw in the log curve and look at y equals x, there they are, and they are those reflections in the y equals x, which we were hoping to see. When you think about it, not a lot of functions are actually going to have an inverse function. Only the ones that are continually increasing or continually decreasing. So a lot of the functions, polynomials for instance, up and down and so on. So what we want to do is restrict it so we can create a 1-to-1 function, and then we can create an inverse. We look at the original function and we pick a piece of the domain where the curve is 1-to-1 for that part of the domain. We'd like as many x values as possible, and 0 if possible. We'd like to include that as well, so we're sort of centered around the origin. Now, y equals x squared, then let's start with that example again. There's y equals x squared. I want to pick a piece of that because the domain at this stage is all real x. Yes, the range is y is greater than or equal to 0, but it won't have an inverse. I want to pick a piece of it. I also want to try and get as much as the range as possible. If I can get all of it, that's fantastic. And for this one, of course, I can. If I pick x is greater than or equal to 0, I will still get the entire range there, and I'll get a piece that is continually increasing. I could, of course, have picked x as less than or equal to 0. That would have created an inverse as well. But we tend to go with the positives. The range now is y greater than or equal to 0. It hasn't changed, but my domain is x is greater than 0. I can now invert it. It'll be y equals x to the power of a half. The domain and range swap round, although it's not immediately obvious on this one because they were sort of the same anyway. But we get that top half of the parabola, which is a reflection in y equals x. But this now gives us another way of finding range of a function, because the domain of the inverse function would end up being the range of the original function. So maybe it's easier to look at the inverse function, because sometimes domain's easier to find than range. So y equals x squared. Okay, we know what that one is, but let's use it as an example. If I swap the x and the y's around, and so I don't get confused between which function I'm talking about, I'll use capital X and capital Y for the new function. Make y the subject. Y is the square root of x as far as the inverse function goes. And if I looked at that, I could say, well, hang on, I know the domain of that function is x is greater than or equal to 0. Therefore, the range of the original function must have been y is greater than or equal to 0. X squared plus 3, again using that idea, swap the x and the y's round, make y the subject. Well, the domain of that would be x is greater than or equal to 3. Therefore, the range of the original one is y is greater than or equal to 3. The absolute value one. Okay, swap the x and the y's round. Now, let's look at that one. A bit hard to make y the subject, but I'm stopping at that point because I know that the absolute value must be positive. So x plus 5 is greater than or equal to 0. The domain of the new function is x is greater than or equal to negative 5. The range is y is greater than or equal to negative 5 of the original function. But we've got to be careful. Y is the square root of 4 minus x squared. If I apply the idea to this one, okay, x would equal the square root of 4 minus y squared. If I make y the subject, I get, oh look, it's the same thing. Y equals the square root of 4 minus x squared. The domain of the new function is between negative 2 and 2. But hang on a sec, because remember we're saying this will be the range of the old function. And if I look at the old function, I know it can't be negative. So I'm not going to take that entire domain to be the range. I'm just going to take from 0 to 2. So we do have to be a little bit careful using this idea. X plus 7 on x plus 4. Okay, swap the x and the y's round. Eventually make y the subject. There it is. But we know the domain of that new function is all real x except x equals 1. Therefore, the range of the original one must have been all real y except y equals 1. Now, would that be a good way for this one? Well, there's a lot of algebra to do there to come up with that answer. Maybe not the best way for that particular one. But as I say, it does give us an alternative way of finding range if something is a little bit tricky. Okay, so 5G.